On the morning of November 26, 2025, at exactly 5:41 UTC, a narrow-band infrared anomaly was detected by the European Space Agency's Thermal Observation Array. It wasn't just another energy burst. It was a localized thermal spike on 3I Atlas's surface, one that should have been impossible at this phase in its orbit. After passing perihelion weeks earlier, Atlas should have been cooling. At over 140 million kilometers from the Sun, its surface temperature was expected to drop steadily, following a predictable radiative curve. Instead, thermal data revealed a sudden 22 degrees Celsius increase, isolated to a region roughly 1.6 kilometers in diameter on the object's trailing hemisphere. The spike didn't build gradually, it appeared instantly, within one 12-second reading cycle, and lasted for 16 minutes before vanishing. There were no accompanying solar flares, no gravitational lensing, no nearby bodies that could account for external heating. The Sun was stable. The environment was quiet, and yet something inside 3I Atlas ignited. That's when things got stranger. The thermal pulse wasn't diffuse, as it would be if sunlight were hitting a rotating surface, or if internal heat was slowly leaking. It was sharply bounded, sharply elevated, and symmetrical, indicating not random heating, but structured release. Multiple observatories were alerted. The La Silla Observatory in Chile confirmed the anomaly using mid-infrared filters. The Gemini North Telescope in Hawaii recorded a brief spike in reflected thermal emissions. Even JWST, though not yet aligned for a full observation, picked up a faint corresponding signal in the 4-micron band, suggesting possible outgassing, though no jets were visible in optical images. And yet there were no visual cues of a surface fracture, eruption, or jet. The shape remained stable. The coma stayed symmetrical. The tail did not change direction. Whatever had released that much energy did so internally. The immediate response among astrophysicists was confusion. One theory proposed internal radioactive decay, but the object's mass and composition, low metal content based on reflectivity, don't support that level of isotopic density. Another theory involved sublimation of buried carbon dioxide pockets, but that would have produced a visible gas release, and no such plume was observed. What remained was a deeply uncomfortable idea: energy storage and release that didn't match any known cometary physics. Something inside 3I Atlas had built up thermal energy, then discharged it in a focused, short-duration burst without external input. A process that sounds far more deliberate than natural. The event timing also matters. Just hours later, 2 other anomalies followed, each building on the previous disturbance. Was the thermal spike a trigger event? A self-test? A calibration routine of something not yet understood? The modelling teams at NASA's JPL attempted to reconstruct the event using synthetic comets in thermal simulation. They failed. No combination of crust thickness, internal porosity, or thermal inertia could produce a short-duration surface spike with that amplitude, unless a phase transition was occurring internally. And not just any transition, something phase-controlled, meaning it reacted predictably under precise thresholds of temperature or pressure. The idea of phase-controlled thermal discharge is not new in materials science. On Earth, it exists in engineered materials, heat shields, memory alloys, and certain reactive polymers. But on a comet from outside the solar system, the implications are profound. If this object is capable of storing and releasing heat with timing and precision, it suggests a system, one that reacts to internal conditions or external triggers. Whether that system is geological, chemical, or technological is still unknown. But what's clear is that the thermal spike wasn't a glitch, and it wasn't a flare. It was a signal of structure, of behavior, and of something happening beneath the crust of 3I Atlas that we're only beginning to decode. For scientists watching the data come in that morning, one thought kept surfacing. Natural objects don't do this. And if this wasn't natural, then the panic wasn't overblown. It was late. At 06:03 UTC on the morning of November 26th, something began to unravel, quietly and almost invisibly, across 3 separate observatories located on 3 different continents. Each was observing 3I Atlas, using their respective arrays, calibrated instruments, and separate protocols. And yet, each reported a measurement that contradicted the others. From La Silla Observatory in Chile came a report of an albedo spike, a sudden brightening of Atlas's surface that suggested a shift in reflectivity or dust composition. The surface appeared smoother, more luminous, almost polished. In infrared wavelengths, this would imply that something had altered the surface layer, perhaps exposing new material or releasing fresher ice. But at nearly the same time, the India-based Astrosat reported a significant dimming in the same spectral window. Instead of a reflective surface, their instruments detected increased absorption. Less light was coming back. Their models interpreted this as surface degradation, possibly the collapse of a jet vent or the layering of dark carbon-rich dust over the active zones. In Hawaii, the Gemini North Telescope provided yet another version. Their polarimetric readings showed a sharp increase in scattered light polarization. That would indicate not just surface change, but reorganization of the coma's dust particles. Polarization shifts occur when light bounces off aligned particles, something that generally only happens when external fields or forces orient the dust. All three measurements were real. All were time-stamped within 7 minutes of one another, and all pointed to opposing realities. This was not a software bug. Each facility double-checked its instrumentation. Internal diagnostics found no faults. Cloud cover, telescope drift, and sun interference were ruled out. The atmospheric conditions were clear, the instrumentation stable. So how can a single object present 3 different observational signatures at the same time? That question alone forced a real-time collaboration across hemispheres. Scientists on encrypted channels began comparing logs, timestamps, and processing methods. They expected to find a calibration error, something simple. They didn't. Instead, what they found was a new kind of inconsistency, a coordinated divergence. Each dataset made sense in isolation. Each matched its location's angle of observation, light entry point, and imaging frequency. But when placed side by side, they created an impossible map. Atlas was, somehow, presenting different electromagnetic behaviors depending on where it was being observed from. This isn't supposed to happen. Light scattering is predictable. Coma composition affects polarization. Jet outgassing changes surface brightness. These are standard variables, and astronomers model them all the time. What they don't expect is a geolocation-dependent light profile, a scenario where the comet looks brighter, darker, and polarized simultaneously, depending on who's watching. That's when an older concept began to resurface in private discussions. Coherent backscattering, an interference effect where light reflecting off structured surfaces creates selective brightness depending on angle. But even that wouldn't explain polarization alignment across hemispheres or simultaneous inversion of reflectivity profiles. There was another hypothesis, more speculative, less comfortable. If 3i Atlas is emitting certain types of electromagnetic radiation in tightly controlled directional beams, narrow bands of reflective or absorptive output, it could be selectively responding to observers. That implies not just passive structure, but dynamic surface behavior, something akin to adaptive camouflage or sensor-facing feedback. In other words, it sees us. Or, at the very least, it adjusts based on who's looking and from where. A chilling concept, one that sent ripple effects through the observatory networks that night. Data normally flows one way, from the object to the instrument. But this time, scientists began wondering if the object itself was participating in the observation. As if Atlas was showing different faces based on geography, like a rotating lens or prism, revealing selective information depending on angle and range. By the end of the day, all 3 observatories agreed on one thing. This was the first time in modern astronomy that a single object had created conflicting truths across the same moment in time. The word that appeared in several private Slack groups among planetary scientists was simple: adaptive. Because when an object changes its signal depending on how you watch it, you're no longer observing a comet, you're interacting with something. At precisely 06:49 UTC on November 26, 2025, the Meerkat Radio Telescope Array in South Africa logged something it wasn't supposed to detect. The array had been scanning hydroxyl emission lines from 3i Atlas, those common signals produced when sunlight breaks down water molecules in a comet's coma. But within those natural signatures, buried just beneath the noise floor, a second frequency layer emerged. This wasn't a burst. It wasn't random interference or solar wind contamination. It was structured, narrow band, stable, repeating. At first glance, it looked like a statistical anomaly. But when technicians filtered out the natural water signatures and aligned the waveforms to isolate residuals, What remained was a modulated frequency envelope, something that suggested purpose, or at least pattern. Hydroxyl emission is predictable. When water molecules are broken apart in space, their components emit radio waves at specific known frequencies, most notably near 1065 and 1667 MHz. That's why astronomers use those frequencies to confirm the presence of cometary ice. But the frequency discovered that morning sat just outside the hydroxyl band, at Thanxston 73.2 MHz. Not a sharp spike, not a beacon, but a pulse train, low amplitude, repeating every 4.2 seconds. The signal didn't oscillate in pitch or amplitude. It didn't encode obvious information, but it was there, and the fact that it remained stable for over 23 minutes across 3 separate antennae eliminated the possibility of local interference. This was not coming from Earth, it was coming from Atlas. Initially, scientists wondered if it could be a natural product of complex outgassing. Perhaps ionized gases interacting with magnetic fields were creating resonant emissions. That theory fell apart quickly. Every known comet, even the active ones like Hale-Bopp or 2I Borisov, emitted dirty, broadband static. Never anything so sharp, so clean, so persistent. Then came the comparative tests. When the same frequency band was aimed at other active objects in nearby sky regions, asteroids, stars, even Jupiter's magnetosphere. No signal. Only when the telescopes returned to 3I Atlas did the pulse resume. Identical frequency, identical spacing, as if it was following its own metronome. Radio engineers ran signal integrity checks. The waveform was tight, low power, and had no Doppler distortion, meaning the signal was either compensating for motion or was somehow directional. That raised another uncomfortable question. How does an interstellar object broadcast in a fixed frequency band with no shift, even while travelling at over 60 km per second relative to Earth? One possibility is that the signal wasn't being emitted at all, but rather reflected. Perhaps Atlas had passed through a background transmission field, like stray emissions from deep space, and its structure had modulated those signals like a prism. But again, the evidence didn't support it. The signal did not match any known transmission from satellites, ground-based facilities, or even past cosmic sources like quasars or pulsars. It was new. Another theory suggested Atlas may possess natural cavities or crystalline structures that resonate at precise frequencies when energy passes through them, like a tuning fork or a quartz oscillator, but that too assumes conditions and materials we've never observed in a comet before. Eventually, the data reached the Signal Verification Subdivision at NASA's Deep Space Network. Their analysis returned one unsettling note. Frequency integrity and temporal structure suggest non-random source, classified as Type C anomaly, sustained, low-band coherent emission from moving celestial body, recommending follow-up triangulation. In simpler terms, this wasn't noise, it was something broadcasting or vibrating on purpose. That evening, a second observatory, Australia's ASKey array, confirmed the same pulse envelope, now fading. The signal was weakening, but the timing matched, the frequency matched, and the implications deepened. Was this a natural resonance, an echo of interstellar formation, or something designed to ride inside familiar emissions, a carrier, a buried signal beneath the noise of nature? By the time the signal fully faded at 0712 UTC, the tone in the control rooms had changed. The astronomers weren't asking if it was real anymore. They were asking why something that wasn't supposed to speak had just whispered once, and then gone quiet again. At 0723 UTC on the morning of November 26th, a high-velocity jet erupted from the surface of 3I Atlas, sudden, clean, and with no visible precursor. In most comets, jets emerge from sunlit fractures or vents when internal ices sublimate and escape as gas. The appearance is typically chaotic, tied to rotation, thermal stress, or crust cracking. But what astronomers observed that morning defied every model. This jet didn't vent from a known fracture. It didn't erupt from a shadowed crevice. It didn't spin into view as the object rotated. It simply appeared directly from the sun-facing hemisphere in a region that had shown no prior signs of structural weakness or thermal instability. And it did so with no delay, no build-up, and no trailing dust fan to suggest a deep cavity or volatile-rich layer had burst. The European Space Agency's HelioViewer system was first to capture the event in full resolution. At 07:23:16 UTC, an ultra-fine jet of material extended outward from Atlas's surface, projected at a near-perfect radial angle, perpendicular to the nucleus. Spectral readings confirm the material was largely carbon dioxide, with minor traces of cyanide compounds and neutral carbon atoms. But the real shock wasn't its composition, it was the speed and stability. The ejection velocity exceeded 2.1 kilometers per second, far above what typical sublimation could account for at Atlas's current distance from the Sun. Most comet jets are barely able to overcome the weak gravity of the nucleus. This one blasted into space like an exhaust plume, narrowing and focusing as it stretched out rather than dissipating into a chaotic spray. Even more unusual, no rotational compensation was observed. In a natural jet, rotation usually causes a sweeping arc in the tail, a spiral or fan-like distortion that marks the slow spin of the nucleus. But this jet remained fixed in angle and position, stable for almost 18 minutes. It didn't track the object's motion. It held firm as if anchored from within. Multiple instruments detected the event, confirming it wasn't a fluke. The James Webb Space Telescope logged a thermal plume consistent with high-energy gas ejection. The Japanese Himawari satellite caught the brief glint of reflective ejecta. Even ground-based amateur telescopes in Eastern Europe caught glimpses of the sudden brightening as the jet's sunlight reflection intensified Atlas's apparent magnitude by almost half a point. And then it stopped. Just as suddenly as it began, the jet collapsed. No residual streamers, no fallback of dust, no new cracks visible. It left behind no alteration in Atlas's surface geometry, no long-lasting coma expansion. The comet simply returned to baseline conditions. So what caused it? Initial theories pointed to deep volatile pockets, pressurized chambers that might have built up internal gas over time. But Atlas had already passed perihelion weeks prior. Thermal expansion should have already vented these materials. There was no heat trigger, no sudden crustal failure, no seismic activity evident. That's when scientists began considering an alternative model, controlled venting. In mechanical terms, controlled venting occurs when internal pressure is released deliberately through narrow channels or valves, systems designed to handle energy build-up with precision. If Atlas somehow contains internal cavities or channels capable of focusing gas release, this could explain the narrow, high-speed jet with no debris fan. But that assumption requires another leap, one that shifts the object's classification from natural to possibly engineered. Because a jet with no surface source, no heat trigger, no dust trail and sustained axial symmetry for 18 minutes is not cometary behavior, it's reactive behavior. Could the jet be a form of propulsion? Could it be redirecting momentum? Could it have been an internal balancing maneuver triggered by forces we don't yet understand? Those who believe Atlas is natural argue for rare volatile configurations, but even they admit this event sits far outside the range of known comet physics. It wasn't a flare, it wasn't a burst, it was a pulse, controlled, symmetrical, and deliberate in its disappearance. And for the teams tracking every micron of movement, it begged a darker question. What happens the next time it fires? At 07:22 UTC on November 26th, a small yet unmistakable signal reached the magnetometer array stationed at Lagrange Point 2. Operated by NASA's Deep Space Solar Weather Division, this station is designed to monitor faint magnetic fluctuations, especially those that originate from solar activity or gravitational disturbances near Earth's orbital rear. What they detected wasn't solar, it wasn't terrestrial, and it wasn't an instrument error. It was an echo. Not sound, of course, but a magnetic mirror, a reflection of a wave that had no known emitter rebounding off empty space. The signal was subtle, a low-frequency oscillation across the sub-microtesla band, appearing once, then again 4 seconds later, then a third time, identical in shape but weakened. The echo's origin point triangulated within a 10,000-kilometer margin to 3i Atlas's projected position. The time delay matched exactly with the estimated travel time for a wave moving at the speed of magnetohydrodynamic propagation through the interplanetary medium. In simpler terms, the magnetic ping lined up precisely with Atlas's trajectory and distance. But here's the puzzle. Lagrange Point 2 sits in a stable gravitational well, shielded from Earth's immediate magnetosphere, but sensitive to disturbances from deep space. It rarely picks up clean returns unless something bounces a signal back. Normally this happens when solar wind is deflected off objects like the Moon or Mars, or when Earth's own field reflects magnetized particles. But 3I Atlas is not magnetic. At least, it shouldn't be. Previous observations indicated low metallic content and no measurable magnetic field of its own. So how did it reflect a coherent magnetic pulse? Scientists proposed 3 initial theories. Passive induction. If Atlas passed through a concentrated patch of solar wind and had enough conductive material, such as surface nickel or embedded iron, then a temporary field could have been induced, creating a magnetic echo. But the signal returned 3 times, and with too much precision. Induction can't sustain that. Magnetized dust shell. Another theory suggests that Atlas is surrounded by a shell of fine dust, ionized by solar radiation, and rotating in such a way that it mimics a weak magnetosphere. If this shell interacts with interplanetary magnetic fields, it could reflect some component of the wave. But again, this doesn't explain the structure or the repeated echo pattern. Active reflection. The third, and most controversial theory, is that Atlas actively emitted a magnetic pulse, either deliberately or as a byproduct of internal activity. The waveform could then have ricocheted through space, hitting the L2 sensor node in staggered intervals due to field geometry. This last possibility caused a stir within NASA's magnetics division, because if Atlas emits magnetic signals, it implies either internal charge separation, sustained electrical activity, or worse, controlled magnetic geometry. In short, not natural. Further complicating things was the timing. The magnetic echo occurred exactly 1 minute after the high-speed jet was observed, and just before the polarization anomalies began to emerge. 3 events, thermal, kinetic, and electromagnetic, all aligning within a window of 60 seconds. This wasn't a coincidence, it was a sequence. The echoes themselves were particularly interesting in their structure. The signal bore a harmonic signature, frequencies nested inside one another, like musical chords, low bass resonance, mid-range pulsation, high-frequency harmonics layered with a decay slope that mirrored engineered signals used in Earth-based magnetic mapping. In other words, patterned. A system that passively emits such a structured echo would be unprecedented in comet science. Nothing about water ice sublimation, jet pressure, or crust fracture can produce a coherent magnetic waveform that bounces through interplanetary space with this kind of repetition. The final report from L2 didn't name it artificial. It couldn't. But it did categorize the event as a Class 4 anomalous reflection, reserved only for magnetic phenomena that originate from deep space and do not match solar or terrestrial sources. Which leaves us with only one conclusion. Whatever passed through the interplanetary medium at 07:22 UTC reflected more than sunlight. It echoed back the universe's most silent force, and something at 3I Atlas was listening. At exactly 8:02 UTC on November 26th, something reappeared that astronomers had been watching for weeks, the anti-tail of 3I Atlas. Most comets have 2 visible tails, one composed of ionized gas blown directly away from the Sun, and another of dust particles gently curved along the object's orbital path. But Atlas had shown something different, something that doesn't belong in traditional comet physics, a sunward-pointing tail. And now, it was back. High-resolution images from the Subaru telescope atop Mauna Kea in Hawaii showed a sharp, needle-like projection extending directly toward the Sun, a phenomenon that had vanished for over a week. The anti-tail was back, but this time it looked more structured, more defined, and disturbingly persistent. Normally, what looks like an anti-tail is an optical illusion, a trick of perspective. When Earth crosses the orbital plane of a comet, the dust left behind can appear to project forward, toward the Sun, when in reality it's just a line-of-sight artifact. That's geometry, not physics. But with 3I Atlas, the anti-tail doesn't follow the rules of perspective. Instead of appearing only during perfect alignment with Earth's orbital plane, the anti-tail remained clearly visible even as viewing angles shifted. Between 0802 and 0840 UTC, telescopes from South Africa, India, and Chile observed the same sharp structure, angled inward, not outward. That should be impossible. The length of the tail extended over 100,000 kilometers, appearing brighter than its previous incarnation during perihelion. It shimmered with particulate composition that reflected in the near-ultraviolet range, uncommon for typical comet dust, which scatters sunlight primarily in the visible spectrum. Spectroscopy revealed its content: fine-grained silicates, nickel particles, and traces of cyanide compounds, similar to those found in Atlas's coma. But their organization wasn't random. The particles followed a tight symmetrical corridor, rather than a diffuse scatter pattern. Worse, radial velocity measurements showed the anti-tail wasn't static, it was flowing toward the nucleus, not away, a reversal of known physics. This observation destroyed the illusion theory. If particles are moving toward the core, then this isn't residual dust caught in a viewing angle, it's an active stream. But what mechanism could create a tail that defies solar wind pressure and gravity? And more importantly, why would a comet eject material in the direction of the sun? That's when researchers began revisiting a disturbing possibility: that the anti-tail is not the result of natural venting at all, but a form of directed expulsion, possibly part of a propulsion cycle. In orbital mechanics, ejecting material against your direction of travel can change momentum. It's the same principle that powers rockets: expel mass in one direction, and you move in the opposite. But Atlas wasn't changing course, it was maintaining its trajectory with unreal stability. So what was the purpose of the anti-tail? Some theorists propose that it may be a method of thermal regulation, a venting pattern to cool the nucleus or redistribute surface stress. Others suggested it could be electromagnetic in nature, with ionized material aligning to fields we haven't mapped yet. But one more explanation quietly circulated in the astrophysics community: that the anti-tail is not an exhaust, but a sensor. If the material being emitted is reflective or contains trace metallic compounds, it could serve as a kind of feedback loop, bouncing solar radiation, capturing magnetic interactions, or even acting as a communications medium. A directional stream to measure or map the star it approaches. That idea flips the entire model upside down. It suggests intention, not randomness, a mechanism, not chaos. When the anti-tail finally faded from visibility just after Uryusin or UTC, it did so without dispersing. The particles collapsed inward, as if being reabsorbed or redirected. No known comet does this. None. For scientists watching across the globe, one chilling phrase kept appearing in their logs and Slack threads. It pointed at the sun, again. At 09:40 UTC on November 26th, telescopes around the world captured a pair of jets erupting from 3I Atlas, symmetrical, narrow, and sustained. The jets were not unexpected. Active comets do this. What was unexpected was how they moved. Instead of remaining fixed in orientation relative to the object's rotation, as every comet jet ever observed has done, these jets repositioned themselves, smoothly shifting angles over the course of 27 minutes, while the nucleus itself showed no detectable spin or precession. This isn't how comets work. Standard comet jets are the result of sublimation, solar heating causing volatile ices within the comet's crust to turn into gas and escape through fractures or weak points. The jet's direction is determined by surface geography, rotation, and sun exposure. When the comet rotates, the jet rotates with it, producing characteristic spirals or arcs in the coma and tail. But Atlas's jets behaved independently. Multiple observatories, including Gemini North in Hawaii, VLT in Chile, and ESA's Solar Orbiter, logged the movement of the twin jets. At first, they were aligned approximately 70 degrees apart, projecting diagonally from the mid-latitudes of the nucleus. But by 0941 UTC, the jets had shifted their orientation by over 15 degrees, both curving in opposite directions and maintaining mirror symmetry. The rotation of the comet flatlined. There was no axial movement sufficient to explain the repositioning, no torque, no wobble. The light curve analysis from the European Southern Observatory confirmed this. The rotation period of Atlas remained locked at its previously recorded 17.6-hour cycle, with no deviation. So how did the jets move? To reposition a jet without moving the surface, you would need one of three things: internal channeling. Imagine pressurized gas being redirected through flexible subsurface tubes or cavities, emerging from new surface vents without requiring surface rotation. But comets are fragile, fractured, and porous. They don't maintain clean sealed tunnels, and no comet has ever demonstrated jet relocation without surface collapse or vent creation. Surface reshaping. Another theory is that Atlas's crust is actively reshaping, rebuilding or closing vents, and opening new ones based on internal heat. But this would require localized melting and restructuring, far beyond the physical capacity of a small icy body at this distance from the Sun. Controlled ejection. The most extreme theory is also the simplest. The jets are being deliberately redirected by mechanisms we don't understand. Not geological forces, not rotation, but something that can reposition thrust without moving the object. This idea isn't without precedent. Spacecraft do this all the time. By vectoring exhaust nozzles or controlling ion thrusters, satellites adjust orientation or momentum without spinning. But for a comet to exhibit similar behavior, it would need complex internal structure, precision guidance, and power regulation. This isn't something you expect from a snowball. Spectral analysis of the jets showed a repeating ejection, pulse, on, every 42 seconds, suggesting some internal clocking or pressure modulation. The particles emitted were micron-scale carbon compounds, unusually uniform in size, moving at consistent velocities. Furthermore, the geometry of the jets was too perfect. As they repositioned, they maintained their angle separation. One curved left, one curved right, and both aligned again by the end of the window, pointing at new vectors as if following pre-calculated trajectories. This symmetry is troubling. It implies coordination, not chaos. Intent, not accident. And when cross-referenced with previous jet events from Atlas, including the infamous November 10th eruption, researchers discovered a repeating pattern. Every time the jets shifted, they did so in pairs. Not random, not single ejections. Always dual, always symmetric. NASA's Jet Propulsion Laboratory issued a private bulletin classifying the movement as rotationally decoupled vector jetting, a phenomenon never before recorded in any natural solar system object. In simpler terms, Atlas is moving parts of itself without turning. For planetary scientists, this is the nightmare scenario, because if a comet is ejecting mass in controlled directions without needing to rotate, it means it has internal systems, and internal systems imply design. The last line of the bulletin, later leaked, said it best. This is not rotation physics, this is behavior. At 10:26 UTC on November 26, 2025, the European Space Agency's Solar System Science Division quietly issued a red flag bulletin. The energy budget for 3I Atlas does not close. In scientific terms, this means that the total amount of energy the object is receiving, primarily from solar radiation, is significantly less than the amount of energy it's putting out through jet activity, heat signatures, particle emissions, and reflected light. The numbers do not add up, and that's a problem. The anomaly wasn't new. Since late October, several ESA teams had been tracking inconsistencies between the observed activity of Atlas and its expected solar input. But what changed on November 26th was that the discrepancy grew wider, not narrower, despite Atlas moving farther away from the Sun. Here are the facts as ESA reported them. At its current distance of roughly 1.46 astronomical units, 3I Atlas receives about 700 watts per square metre of solar radiation. With an estimated spherical diameter of 5.6 kilometres, the object's cross-sectional area intercepts roughly 17.6 million watts at peak exposure. Even under the impossible assumption of 100% absorption and zero loss to albedo, i.e. a black body, this is the theoretical upper limit of energy available for activity. And yet, Atlas is outputting jet activity that ejects billions of kilograms of gas monthly at escape velocities exceeding 2 kilometers, internal heat pulses that spike regional temperatures by 15 to 20 degrees Celsius in minutes, electromagnetic signatures at specific frequency bands that require sustained power to maintain, a coma that is expanding even after perihelion, with increasing particle density and tail length. When the math was run, ESA's models estimated Atlas to be expending nearly 4 times more energy per hour than it could possibly be receiving from solar radiation alone. That's not just a small deviation, that's a collapse in physical modelling. At first, researchers tried to explain this by proposing internal heat reserves. perhaps pockets of radioactive materials or long-trapped volatiles that were now releasing stored energy. But the sustained, rhythmic nature of the jets made that theory weak. Radioactive decay is chaotic. Sublimation is sensitive to surface exposure. Atlas is displaying structured consistency. ESA's simulations were clear. This activity cannot be natural without invoking physics we don't yet understand. What really rattled mission scientists was the timing. Just hours earlier, Atlas had displayed unusual jet repositioning behavior and re-emergence of its anti-tail. Now, with these energy outputs being tracked in real time, it became clear that some form of onboard regulation must be controlling the flow. Because the output wasn't random, it was timed. An internal memo from the ESA's Comet Dynamics team made the comparison explicit. If this were an Earth object, we'd call this a reactor operating at near full capacity. The power profile shows no expected taper. If anything, it's increasing. More troubling was what ESA called non-thermal coherence. Normally, a comet's energy loss is diffused, scattered across many frequencies. But Atlas is selectively emitting heat, electromagnetic pulses, and visible light in tight, predictable bandwidths. That's a signature not of a melting object, but of a system with energy focus. In short, Atlas is behaving like an engineered system, or at least something with internal mechanisms that can control, regulate, and redirect energy far more efficiently than natural ice and rock ever could. One physicist on the team reportedly muttered the words, "It's generating surplus," during the call. And that concept, the idea that something in deep space might be drawing, storing, or even generating more energy than it receives, is terrifying not because it's impossible, but because it's measurable. The numbers don't lie. The object is outperforming physics, and the scientists for once have no words left to bend the math. At 12:03 UTC on November 26th, the pulse returned. It wasn't light, it wasn't heat. It was something subtler, a spatial rhythm, a silent heartbeat inside the coma of 3I Atlas. This phenomenon, now referred to by multiple observatories as a geometric pulse, had first been seen weeks earlier during Atlas's approach to perihelion. At that time, scientists noticed repeating structural changes in the surrounding gas cloud, forming symmetrical patterns at regular intervals. Then it stopped, until now. This time it came back stronger, more defined, and unmistakably deliberate in its structure. Using data from the Very Large Telescope in Chile and corroborated by the James Webb Space Telescope, researchers identified a repeating triangular emission pattern inside the ionized shell of Atlas. Every 9 minutes, 3 small jets would erupt from the nucleus, equidistant, both in angle and spacing, 1, then 2, then 3. Always in the same sequence, always from the same locations, always maintaining a perfect 120-degree separation. Each pulse lasted 23 seconds. Each emitted material in micron-thin filaments. Each displayed velocity uniformity to within a margin of less than 2%. This is not turbulence. In physics, symmetry almost always hints at structure. Random outgassing can produce temporary shape, but not repetition. Not like this. You cannot get synchronized ejections from a porous comet without an internal mechanism. Something that fires, reloads, and fires again. One researcher described it bluntly. It's like watching a 3-engine system run a loop. Further analysis showed that the ejection points weren't just stable in surface coordinates. They were aligned in 3D space, maintaining consistent orientation relative to the Sun, not relative to Atlas's own slow axial rotation. That defies physics as we understand it. For jets to stay locked in heliocentric orientation, while the body spins, requires either continuous course correction or a feedback system that knows where the Sun is. The implications deepened when JWST tracked fine dust layers expelled during the pulse events. The dust didn't disperse randomly. It formed nested spirals like tiny magnetic vortices, suggesting a second layer of organization, possibly electromagnetic. Radio telescopes simultaneously detected low-band frequency oscillations during the same time intervals, further linking these pulses to a broader energetic signature. This wasn't just a visual show, it was a multispectral event, with thermal, visual, and magnetic fingerprints all peaking together. The timing, 9 minutes exactly between events, also raised eyebrows. Comet activity doesn't run on clocks. It responds to heat gradients, stress fractures, random sublimation bursts, not timers, yet this pulse did, consistently, predictably, quietly. The European Space Agency ran time series analysis on all previously logged events and found something chilling. The same 9-minute interval had occurred twice before but had gone unnoticed due to resolution limitations. The November 26th event was simply the first time all instruments were watching at once, at high enough fidelity. Why 9 minutes? No one knows. But systems that repeat on intervals tend to fall into two categories: oscillators or engines. And neither word sits comfortably inside a sentence about a comet. The geometry too was disturbing. A triangle isn't a natural shape in astrophysical gas emissions. It doesn't arise from random fracturing. It doesn't emerge from symmetrical heating. It requires placement, 3 sources arranged equidistantly, each firing with the same thrust profile and timing offset. It's architectural. The theory proposed in closed-door scientific discussions is that the pulses may serve a navigational or orientation purpose. Small course corrections, balance maintenance, or worse, signalling. One astrophysicist from the Institute for Radio Astronomy in Bologna quietly asked, "What if the object isn't just stabilizing itself, but syncing with something else?" No answer was offered, because when the pulse returned on November 26th, the data stopped feeling like observation. It started feeling like interaction. At 12:39 UTC on November 26th, astronomers across 3 continents noticed something strange. The brightness of 3i Atlas dropped, sharply, within seconds after one of its most forceful jet ejections, not gradually, not like a shadow, but as if something turned off a light. Using photometric analysis from both Earth-based and orbital telescopes, scientists recorded a 24% decrease in apparent magnitude within a 7-minute window following the jet event. This wasn't dust spreading to obscure the nucleus. It wasn't a change in solar angle. The coma's overall shape remained consistent. Only the reflectivity dropped, dramatically. This is not how comets behave. Typically, when a comet ejects material, it becomes brighter, not dimmer. Sunlight hits the new dust, causing scattering across multiple wavelengths. The coma grows, the tail intensifies, the brightness spikes. But here, the opposite occurred. Immediately after the jet activity, identified as a dual vent ejection near the object's southern terminator, the coma surrounding Atlas collapsed inward. Spectrometers detected a sudden loss of reflectivity across the ultraviolet and visible spectrums. In practical terms, it was as if the material went dark. There are only a few natural explanations for a reflectivity drop like this. Absorption by carbon-rich dust. Some comets eject dark material, like soot or complex hydrocarbons, which absorb more sunlight than they reflect. But Atlas had previously shown a high albedo, with silicate-based dust dominating the spectra. A sudden transition to dark material would require a major surface rupture, which wasn't observed. Rapid dust recombination. If ejected particles clump together fast enough, they can reduce surface area and lower reflectivity. But this process takes hours or days, not minutes. It can't explain a near-instant collapse in brightness, reabsorption, or containment. The most controversial theory is that the material wasn't lost. It was pulled back or otherwise masked by some form of field or containment envelope. This isn't comet science, it's spacecraft engineering. Infrared sensors noticed something else. While the visible and UV reflectivity dropped, the thermal signature remained active. In fact, it intensified. The jet had released a surge of heat, but the dust it expelled didn't radiate as expected. Instead, it appeared to vanish from view, while still emitting in the far infrared. This mismatch, high heat, low light, is deeply anomalous. It suggests that the dust didn't dissipate, it simply changed its optical state. One possibility raised in internal reports is phase shifting. Microscopic particles altering structure after ejection, changing their refractive index in response to localized energy fields. Another is electrostatic charge clustering, creating low scatter shells that absorb light from within. The most speculative proposal was this: a shielding effect. The material expelled may be coated or bonded in a way that allows it to absorb energy, re-radiate in controlled bands, and effectively cloak its visual profile. Not unlike stealth coatings on modern aircraft, only far more advanced. The data timeline only deepens the mystery. 12:36 UTC, jet activity begins. 12:37 UTC, brightness begins to drop. 12:38 UTC, UV scatter disappears. 12:39 UTC, visible coma dims by 24%. 12p43 UTC, thermal signature remains elevated. 12p50 UTC, reflectivity begins to return but not fully. That last detail is crucial. The brightness never returned to baseline. Even 30 minutes later, Atlas remained 13% dimmer than pre-ejection levels, suggesting either partial particle loss or persistent masking. For the European Southern Observatory, this event forced a reclassification of Atlas's photometric behavior. It is now listed as a variable phase object, a category normally reserved for near-Earth asteroids or artificial satellites, exhibiting panel or rotation-based reflectivity changes. But Atlas has no known panels, which leaves one possibility. It's not the light that changed, it's the surface reacting, intentionally or not, to what it just did. And now, for the first time, scientists are forced to ask a disturbing question. What kind of object gets darker after it moves? At 14:18 UTC on November 26th, deep field observations from both ESA's Solar Orbiter and the James Webb Space Telescope converged on a single, baffling conclusion. The coma surrounding 3I Atlas had tripled in particle density in just under 30 minutes. This was not a linear growth, it was an exponential surge. Cometary comas are diffuse halos of gas and dust expelled from the surface as solar radiation heats volatile compounds. Typically, coma evolution follows a predictable pattern: slow growth during approach to the Sun, rapid expansion near perihelion, and gradual dispersal as the object moves away. But what happened with Atlas wasn't gradual. It was a sudden, violent inflation of the surrounding space, without the heat spike to justify it. Ground-based measurements from the Atacama Large Millimeter Array, ALMA, showed a coma mass increase of 0.3% from 14:18 to 14:47 UTC. That figure was independently confirmed by infrared scattering models and light curve decay readings from JWST's NER-SPEC instrument. But there's something even stranger. There was no corresponding increase in brightness. Usually denser coma, brighter object. More particles mean more light scattering. Instead, Atlas remained optically stable. The coma grew, but its overall reflectivity plateaued, suggesting either non-reflective material or some form of absorption within the cloud itself. What could explain this? One theory proposes that the particles being ejected were supercooled, released from subsurface reservoirs in a sudden pressure event, then forming a dense but dark cloud. These particles may be primarily composed of high molecular weight hydrocarbons, or metallic dust, both of which are poor optical scatterers. But that only solves half the mystery. Because JWST picked up a disturbing signal, structured layering inside the coma. The dust wasn't evenly distributed. It was appearing in shells, concentric rings radiating from the nucleus at fixed intervals, each separated by approximately 240 kilometers. Shelling of this kind has only been observed once before, from the artificial release of ejecta during the Deep Impact mission on Comet Tempel 1. That event was controlled, timed, and directed. Atlas's version? It came from nowhere. Spectral readings during the event revealed a sharp spike in trace elements, particularly sodium and nickel, both indicators of deep interior material. This led researchers to conclude that the surge in coma density wasn't caused by gradual sublimation, but rather by the opening of internal chambers, as if something beneath the surface had unlocked, released, and sealed again. And the timing was coordinated. The tripling of the coma occurred minutes after Atlas displayed another round of geometric jet repositioning. The symmetry of the ejections paired with the volumetric release points to a structured system, not a fractured rock. Even more telling was the directional consistency of the expansion. The densest regions of the coma formed along the same axis as previous jet paths. This means the ejection was not omnidirectional, like an explosion. It was vectorized. One scientist compared it to a balloon inflating along pre-drawn lines. A second layer of confusion came from magnetometer readings aboard Solar Orbiter. As the coma density tripled, a measurable drop in local magnetic resistance was recorded, suggesting that the particles were either conducting or interacting with the solar wind in non-standard ways. This was not dust behaving like dust. The final twist. After 1447 UTC, the density stopped increasing. Abruptly, cleanly, like someone closed a valve. No natural process turns on and off that fast, not without detectable thermal flux or continued stress fracturing. So we are left with this, a comet that suddenly increases its coma mass threefold, without rotating, without heating, and without brightening, then stops. No tail disruption, no impact event, no solar flare, just silence, and a vastly more massive cloud. And yet, through it all, the nucleus of Atlas remained perfectly centered. No drift, no spin increase, no sign of recoil from the massive outgassing, which means the momentum from that material, billions of kilograms of matter, was either absorbed or countered. And that's when astronomers began whispering the one word no one wanted to say: stabilized. At precisely 15:12 UTC on the morning of November the 26th, a set of coordinated telescopic arrays across Hawaii, Chile, and orbit triggered a level 3 chemical alert. The concentration of hydrogen cyanide, HCN, in the coma of 3I Atlas had spiked by a factor of 6.2 in just under 11 minutes. This wasn't just a fluctuation, it was an atmospheric event with intent. Hydrogen cyanide is not unknown in comets. It's a volatile organic compound, often released from deep-buried ices as sunlight begins to sublimate the surface. But even in the most active cometary bodies, HCN release is gradual, noisy, and chaotic. Atlas, however, delivered it in a pattern, dense, stable, sustained, and with no preceding thermal cue. The European Space Agency's spectroscopic data showed a clean HCN signature emerging from a single vectorized source on the object's equatorial region. Not multiple vents, not diffuse jets, one specific emission zone. It began as a whisper, barely above background levels, and then escalated rapidly, peaking in less than 600 seconds. No corresponding spike in heat, no burst in visual brightness, just molecular emission, as if the object had opened a valve, released its payload, and closed it again. This type of chemical behavior prompted scientists to consider two deeply uncomfortable possibilities: internal regulation, that 3I Atlas possesses either pressure compartments or a subsurface lattice designed to isolate and time the release of certain compounds; catalytic triggering, that a process beyond thermal sublimation is guiding the reaction, possibly driven by electrochemical or magnetic mechanisms. The spatial distribution of the HCN cloud added more intrigue. High-resolution analysis from JWST's MIRI instrument showed that the molecules formed a tightly bound torus, rotating gently around the nucleus before diffusing outward. That configuration shouldn't exist naturally. HCN should disperse quickly into the coma, especially under the influence of solar wind. But this torus stayed intact for over 37 minutes. One planetary chemist described the pattern as artificial containment without a container. As always, nature was consulted first. Some suggested that charged dust within the coma could be stabilizing the HCN through static clustering. Others proposed temperature inversions in the local space environment that slowed diffusion. But all those theories fell apart under the same flaw. None of those conditions existed that day. Solar wind was low, ambient plasma temperature was uniform, the local magnetic field was stable. In other words, there was nothing out there holding the HCN together. And yet, it held. This wasn't the first time HCN had spiked from Atlas. A smaller incident was recorded back on November 14th, though its scale was lower, and it was dismissed as a possible processing artifact. That event now appears to have been a test pulse, a precursor, or worse, a calibration. The implications are vast. Hydrogen cyanide is not just a toxic molecule, it's a prebiotic agent. On Earth, it has been linked to the early formation of amino acids and nucleotide bases, the building blocks of life. That means any object actively managing and releasing HCN in a structured way isn't just a rock with gas, it's a chemistry platform, a reactor. Some have quietly speculated whether the surge is meant to interact with nearby planetary atmospheres or dust fields. Others wonder if it's a form of internal pressure regulation, perhaps part of a broader cycle yet to be understood. But one idea now creeps into discussion rooms: communication. Could timed chemical release be an encoded message? Not for us, but for something else in deep space. So far there's no proof, but on the morning of November 26th, for 11 straight minutes, 3I Atlas exhaled one of the deadliest, yet most cosmically significant molecules known to science, and it did so with elegance, precision, and silence. At exactly 16:07 UTC on November 26th, the Solar and Heliospheric Observatory, SOHO, registered a sudden localized dimming in the optical nucleus of 3I Atlas, something that had never been observed before. The brightest central region of the object, typically flaring with diffuse reflections and occasional jet flickers, was now exhibiting a clearly defined dark zone, not a shadow, not a gap in data, but an actual absence of light from within the comet core itself. Infrared imaging from the James Webb Space Telescope followed within minutes, confirming what SOHO had suspected. The central region of 3I Atlas had dropped in temperature by 12 Kelvin in under 4 minutes, and its albedo, its reflectivity, collapsed by over 40% in that region. In simple terms, a piece of the core had gone completely non-reflective and thermally dead. No rotation accounted for it. No external object had passed between Atlas and the Sun. There was no plume, no ejection, no dust screen to block it. It was as if a door had closed inside the comet. The dark zone spanned approximately 2.1 kilometers across and maintained a stable circular geometry. Even as the surrounding coma remained active, glowing and undisturbed, this section of the core remained locked in place, visually inert and absorbing. Spectral analysis revealed even more strangeness. Normally, areas of low reflectivity on cometary surfaces correspond with carbon-rich deposits, often mixed with volatile ices. But this zone had no expected signatures. It didn't reflect invisible light, nor emit in mid-infrared. It was as if it wasn't there at all. Some researchers proposed that this might be a form of surface delamination, where a layer of material collapses inward, forming a shallow depression that hides the hot inner surface. But that would still show up in infrared as residual heat. Others suggested that a shell of unknown material might have extended outward and occluded the view. But even that theory breaks under scrutiny. There was no movement, no outward shift, no expansion into the coma. The dark zone didn't grow, it simply appeared, and just as troubling, it stayed. For nearly 51 minutes, the region remained completely non-reflective. No thermal re-radiation, no high-frequency backscatter. The surrounding nucleus even showed elevated sublimation rates, suggesting internal activity continued. But whatever was happening beneath that dark circle, the data couldn't reach it. The psychological effect on observers was palpable. This wasn't just another chemical anomaly or geometric jet. This was an absence in the most literal sense. Something in the core had gone silent, and then, without any transition event, the zone vanished. At 16:58 UTC, it returned to baseline. The temperature rose, the light reflectivity recovered to 92% of original. But unlike typical thermal diffusion or outgassing recovery, this return happened all at once, within a 10-second telemetry window, almost like a lid being lifted, and now, speculation deepens. Was this a temporary shutdown of internal systems, a sensor occlusion caused by internal rotation, or something more intentional, an active mechanism retracting into the core? Engineers analysing the signal compared the light curve to aperture behaviour, like a camera iris, narrowing and then expanding again. But in a comet nucleus, no such mechanism should exist, and yet the data remains, an area of complete absorption, no ejection, no debris, no heat bloom, just a perfectly still, perfectly round hole in the light, on a comet that continues to defy everything we know about physics, chemistry, and design. At 17:46 UTC on November 26th, a silent alert was triggered inside the Jet Propulsion Laboratory's Orbital Trajectory Simulation Suite. The models had diverged. According to gravitational calculations, solar pressure modelling, and all current data from both ground-based observatories and solar probe flybys, 3I Atlas should have deviated by 0.0043 degrees in its inertial trajectory. It didn't, not visibly. The numbers were clear, the output was precise, but every optical and radar confirmation showed no measurable positional change. This wasn't a computational error, it was a physical contradiction. A comet of Atlas's mass and coma density, interacting with solar radiation and exuding material jets in 3 directions, should exhibit microcourse corrections. Every jet should cause a minor natural recoil. That's standard Newtonian physics. But here, it was as if those corrections were being absorbed, neutralized, or redirected. Solar Orbiter's magnetic envelope simulations further compounded the mystery. They showed that the surrounding plasma field was behaving asymmetrically, as if something was moving, yet leaving no trace in spatial displacement, a kind of phantom momentum. One hypothesis emerged from the orbital analysis teams: counterthrust. Not the accidental kind, like chaotic ejections from a tumbling object, but precision-aligned energy discharges, matching the vector and intensity of the expected trajectory changes, cancelling them out. That idea would make sense on a spacecraft, not a comet. More conservative voices suggested it might be an anomaly in our observation frames, that perhaps some curvature of the light path, caused by electromagnetic distortion or solar gravitational lensing, had tricked the sensors into thinking the comet hadn't moved. But those theories failed under cross-reference. Infrared telemetry, LIDAR pings, and optical triangulation all confirmed the same thing. 3i Atlas remained perfectly on track, even when it shouldn't have been. And there's a chilling footnote to the event. The deviation that was calculated had a profile. Not random drift, not a chaotic meandering path, but a clean vector arc, mimicking the kind of shift used in orbital insertion maneuvers. It resembled a controlled curve, the kind executed by spacecraft when approaching a gravity well, like Jupiter or a planetary moon. Which raised the deeper question: what trajectory is 3i Atlas trying to follow? If it's actively resisting deviations caused by natural forces, that implies guidance, and guidance implies intent. This wasn't the first time such behaviour had been suspected. Earlier in the month, mission control teams had flagged irregular solar wind interactions near the object, but those were dismissed as turbulence. Now, with clean calculations showing expected drift, and clean visuals showing none, the tension had become unavoidable. The object was behaving like it had inertial dampening, the kind of system that absorbs or redistributes force internally, keeping external movement in check. Something not just passive, but responsive. If 3i Atlas is absorbing motion and maintaining a mathematically impossible path, then we are no longer tracking a body bound only by gravity and chance. We are observing a navigation event, and here lies the most disconcerting part. The orbital deviation was corrected before it happened. Telemetry logs show that the predicted drift never began. That means the object either knew the force vectors acting upon it before they were applied, or it is actively recalibrating its trajectory in real time based on feedback far more advanced than anything in human systems. To course correct before motion requires anticipation, and now, for the first time, mission analysts had to write a word in their margin notes that hadn't been used in any official cometry study before: autonomous. At 1826 UTC on November 26th, a faint yet undeniable glow was spotted trailing 3i Atlas across a portion of space deep within the sun's shadow, a region where sunlight shouldn't reach and where no reflection should be possible. Yet there it was, stretching nearly 3,000 kilometers behind the object in a thin, iridescent strand. Astronomers initially dismissed it as data artifact, perhaps light bleeding from a background star or instrument scatter. But cross-reference from 3 independent instruments, including JWST's Forward Occultation Lens and the Solar Terrestrial Relations Observatory, Stereo B, confirmed the event. The noctilucent trail had reappeared. Noctilucent clouds are typically an Earth-bound atmospheric phenomenon, formed when ice crystals reflect light from below the horizon, creating luminous patterns high in the mesosphere. But in this context, the term has been adapted for deep space use, a reflective trail that glows in shadow. That shouldn't happen. The region where Atlas was travelling was entirely in the sun's lee, behind both heliospheric plasma interference and light-blocking geometry. This means no direct solar photons were present, and yet the trail shimmered, clearly composed of small aligned particles reflecting or refracting light that, by every known physical law, should not be there. The material itself appeared sub-micron in scale, behaving like high-altitude aerosols but arranged in a precise arc. Imaging showed the trail wasn't diffusing, but rather rotating slightly in sync with the comet's position, as if tethered or at least coordinated with the body's movement. This trail was not new. A similar structure had appeared 12 days prior, shortly after Atlas completed a high-velocity tail reconfiguration near Venus's orbital plane. At that time, the trail had been seen briefly and dismissed as residual charge dust. Now, its reappearance under zero solar illumination forces a re-evaluation. If sunlight isn't illuminating it, what is? One possibility: non-visible radiation. Some scientists now suspect that the trail is responding not to photons, but to energetic particles, perhaps even using local cosmic rays or solar wind backscatter to activate phosphorescent compounds. But the chemical composition of cometary dust shouldn't allow for that, unless, of course, it isn't cometary dust at all. Spectral reflectometry revealed a disturbing clue. The reflectance peak of the trail material was centered around 427 nanometers, a wavelength rarely seen in natural dust but commonly associated with engineered polymers under UV excitation. This suggests either a novel compound or, more radically, structured micromaterials. Such precision would be astonishing for any natural process. But the kicker came from radar sweepbacks conducted by NASA's Deep Space Network. As the trail persisted, it generated a faint but regularly pulsing echo, indicating a repeating density pattern every 93 kilometers. That's not noise, that's architecture. Some compared it to a breadcrumb trail, a navigational or signaling mechanism left behind in low radiation space. Others noted its coincidence with earlier magnetic wave shifts, wondering if this glowing arc is not just residue, but part of a larger feedback or transmission system. And then comes the question no one wants to ask. If this trail reappeared in darkness, what is it for? Natural sublimation doesn't create symmetric, glowing material in shadow. Charged dust doesn't hold coherence for thousands of kilometers, and no known comet leaves a luminous trail that seems to follow intelligent spacing logic. The trail dimmed around 1844 UTC, fading not abruptly but gradually, like a signal fading out rather than particles dispersing. There were no jets, no solar flare, no trigger, just the appearance of light, where light had no business being, and then just silence. At precisely 19 Usursuntus or UTC on November 26th, an anomalous return signature was logged by ESA's ROAM-2 deep resonance platform, which had been monitoring 3I Atlas using low-frequency acoustic scatter techniques. What it recorded wasn't expected. It wasn't noise, it was a patterned internal echo, emerging from within the comet itself. The instrument was designed to scan for density pockets and voids by bouncing long-wave low-energy pulses off the nucleus and reading the response time. Comets, being loosely packed icy rock aggregates, normally produce diffuse uneven echo profiles like tapping on a gravel pile. But this time, Atlas responded like a bell. The echoes returned in a triadic interval, 3 major peaks at precisely 14.6, 29.3, and 44.1 seconds apart. That means the internal structure of 3I Atlas is reflecting sound in a regular tiered formation, suggesting stacked density layers, possibly even compartments. This contradicts everything we know about cometary composition. Standard models predict radial heterogeneity, chunks of frozen gases, dust, and rock in chaotic mix. But what we're seeing in Atlas now looks engineered. Each returning wave peak was clean, no diffusive bleed, no absorption wobble. Instead, the internal echoes amplified, meaning the signal was bouncing inside hollow structures that resonate with coherence. Researchers at Caltech ran the ROAM-2 dataset through architectural acoustic modeling. The simulations came back with jaw-dropping similarity to multi-chambered domes, like fluid tanks or pressurized vaults. The spacing of each echo indicated hard boundaries, not porous layers. One astrophysicist summarized it like this: "This doesn't sound like a comet. It sounds like a cavern with tensioned walls." And then, a secondary detail added new weight to the discovery. For exactly 6 minutes, the resonance pattern continued without deviation, then abruptly shifted, as if the internal geometry of the object had changed. The delay between the second and third echoes compressed by 1.8 seconds, implying that one of the reflective boundaries had either moved closer to the surface or folded inward. How does a comet shift its internal walls? No thermal spike was observed, no external impact, no rotational stressor. Just a change. That left the external shape of Atlas completely unaffected. One hypothesis suggested internal magnetic realignment, like ferrofluid shifting inside a container. That would require a field strength vastly higher than anything observed in Atlas's environment. Another posited collapse of a subsurface chamber, but such an event would have caused a dust jet, a thermal bloom, or at least a brightness change. None occurred. And then came the radio anomaly. During the echo event, a narrowband radio pulse at 13.7 kHz spiked twice, timed exactly with the echo intervals. No known spacecraft in the region transmits at that frequency. It's a non-communication band, but one sometimes used in Earth-based submarine resonance systems for sonar calibration. In other words, it's a frequency used to listen for structure. Was this a coincidence? Or was something inside 3i Atlas responding to the scan? So far, the official statement is muted. Agencies admit that internal echoes have been detected but claim they're caused by unusual density stratification, perhaps due to past perihelion events or layered volatile formation. But behind closed doors, the language is shifting. Internal chambers, pressure resonance, structural echo control, not words you'd ever use for a natural object. And now, new questions loom. If these internal structures exist, what is their purpose? Pressure equalization, material storage, or something far more deliberate, a compartmentalized design for energy, matter, or even signal processing? Whatever the answer, one thing is now certain. 3i Atlas doesn't just reflect light, it echoes, and what it echoes back sounds unnervingly organized. At 1951 UTC on November 26th, a flagged anomaly was transmitted to the mission team at the Space Telescope Science Institute in Baltimore. The James Webb Space Telescope's MIRI instrument, designed to scan mid-infrared emissions with unparalleled precision, had captured something that defied all cometary behavior. A region near the center of 3i Atlas's nucleus returned zero infrared response. Not low, not muted, none. This wasn't a calibration error. The rest of the image was intact. Heat from dust jets, thermal gradients across the coma, radiative leakage from gas trails. Everything else was normal, but this one patch was black. Nicknamed the Dead Zone by the MIRI calibration team, it measured just under 1.2 kilometers in diameter, sitting offset from the rotational axis. It wasn't a shadow. Atlas was in full phase, and it wasn't ice. The signature lacked the telltale, reflective cold peak seen in frozen patches. It was something else entirely. At this specific wavelength band, between 12 and 15 microns, every known material, even in deep space, emits at least a faint thermal signature due to background heating or internal friction. But this zone absorbed everything. No re-radiation, no scatter, no echo. It was as if MIRI was staring into a perfect null point. To make matters more unsettling, the dead zone didn't remain static. Over the next 11 minutes, JWST tracked a slight morphological shift. The zone elongated, then contracted again, as if flexing. But the movement was not in sync with the object's rotation or known internal dynamics. One astrophysicist described it as watching a mask on the comet's surface reshape itself to avoid detection. But even more disturbing than the visual void was the spectral cutoff. Within the dead zone, all wavelengths in the mid-infrared were suppressed. No trace molecules, no gas bloom, no temperature differential. And yet, the zone sat embedded in an otherwise active area of the nucleus. This raised an alarming question. Is something within 3i Atlas blocking the signal on purpose? Some scientists speculated the presence of a metamaterial, an engineered lattice capable of redirecting radiation through destructive interference. In human terms, we've developed such materials for stealth aircraft and cloaking prototypes. But this would require microscopic precision on a rotating comet core, tens of millions of kilometers from Earth. Others proposed a nonlinear absorption matrix, an exotic form of matter that only absorbs specific wavelengths, perhaps as a form of energy conversion or insulation. And yet another theory, whispered, not written, suggested the dead zone is not a material at all but a window, a surface aperture or active veil concealing an internal system that must remain thermally hidden. Because during those 11 minutes, the zone not only persisted, it avoided alignment with JWST's direct gaze. This means 3i Atlas either reoriented slightly, or the zone itself shifted laterally across the surface, as if it responded to being observed. When the object rotated again to the same position 2.4 hours later, The dead zone was gone. That's not how surface features behave. You don't just turn off a region of a comet's thermal map, especially when the surrounding area is undergoing outgassing. NASA and ESA haven't released a formal explanation, but internal notes from the MIRI telemetry team now refer to this as a null albedo response event, a phrase not used in any other celestial body documentation. And within deep space physics circles, one quiet conclusion is beginning to surface. If you can turn off your thermal signature, you're not just surviving the cosmos, you're hiding inside it. At exactly 2013 UTC on November 26th, a sudden pressure ripple was detected by the Solar Dynamics Array orbiting at Lagrange. Point 1. The anomaly emerged not from the Sun, but from behind 3I Atlas, specifically from the outer sheath of its plasma tail. For 12 full seconds, instruments recorded a shockwave propagation that moved outward from the tail, forming a concentric arc at nearly 18 kilometers per second. This ripple did not originate from solar wind. It did not correspond to any known jet emission or flare interaction. It emerged from the tail itself, like a pulse from within. At first, analysts assumed it was a flare deflection artifact, but modelling eliminated all solar origin scenarios. Instead, what became clear was this. The shockwave was self-generated, and it moved perpendicularly across the tail structure, not along it. This defies everything we understand about cometary physics. Tails are formed by the solar wind stripping gas and dust off a comet's nucleus. These tails are directional, fragile, and passive. They do not generate internal pressure waves, let alone ones that can be tracked from 700,000 kilometers away. So what did we see? When the full data spectrum was analysed, it revealed a multi-layered profile, a thermal uplift, a magnetic deflection, and an acoustic signature compressed into a single moving front. In other words, the wave acted like a structured energy packet, something designed to move with purpose, not randomly. The propagation pattern mimicked ripple behaviours seen in plasma waveguides, where a sudden energy discharge travels along an ionized path without scattering. Yet the tail of 3I Atlas is not a stable conduit. It shifts, it curls, and yet this wave moved with perfect curvature, matching a spiral that aligns with the comet's prior rotational vector from 2 days earlier. That's not accidental geometry. Even stranger was the response. The moment the shockwave passed through the far edge of the tail, the coma flared, registering a 0.8% increase in density across a lateral axis of 4,100 kilometers. The material didn't get pushed away. It compressed inward, as if drawn toward the core. This is the opposite of what should happen in a shock event. A natural shock disperses particles, but here the tail collapsed momentarily inward, tightening like a drawn cord before expanding again in its usual formation. There was no accompanying jet from the nucleus, no solar CME, no collision, only a silent ring moving outward and a tail that folded slightly, then reset, as if instructed. Later comparisons were made to synthetic impulse bursts, energy pulses used in laboratory conditions to trigger synchronized reactions in distributed plasma arrays. But there is no known cometary context where such a pulse should arise naturally. Moreover, the frequency of the wave was unnerving, precisely 28.14 MHz, consistent across every instrument. That's not a chaotic emission, that's a calibrated output. Even more unsettling was the angular symmetry. The shockwave, when visualized in 3D, formed a hexagonal front, breaking the standard diffusion shape. It wasn't just a pulse, it was a patterned release, hinting at internal control or guidance. As of now, official observatories remain cautious in their language. The event is being referred to as an anomalous electromagnetic tail compression. But behind closed doors, multiple labs have flagged this as the first possible instance of active plasma modulation originating from an interstellar object. That is not cometary behavior. That is system response. And now the question stands, if Atlas can generate structured waves through its own tail, what else is it capable of coordinating across vacuum, plasma, and field? The ripple wasn't just a wave, it was a message in motion. At 2039 UTC on the night of November 26th, the Haleakala Polarimetric Array in Hawaii reported a startling observation. The polarization angle of light coming from 3I Atlas had shifted and locked into perfect alignment with the object's long axis. This wasn't expected, or even thought possible. Under standard conditions, light reflecting off cometary surfaces scatters chaotically. Dust particles, gases, and jets distort the polarization field, producing a randomized pattern that fluctuates with solar angle, rotation, and jet emissions. But in this case, the polarization didn't just stabilize, it organized. Over a 10-minute window, the scattered light around 3I Atlas formed a coherent plane of polarization, extending across the coma and jet structures. The orientation vector matched the object's rotational pole within 0.7 degrees. That level of alignment is unprecedented. To observers, it looked as if the object had suddenly become a polarizing filter, channeling incoming light into a single organized state. But this is impossible for a natural body with no fixed surface, no atmosphere, and no refractive crystal shell. So how did it happen? Spectropolarimetric analysis revealed something even more confusing. The polarization wasn't limited to reflected sunlight. Portions of it were generated from secondary light scatter within the coma, suggesting that particles themselves were rotating in unison, acting as microlenses or aligned dipoles. This would require torque on the dust grains, something to force orientation across tens of kilometers of diffuse cloud. But 3I Atlas was not experiencing a solar wind spike. No magnetic event was detected. There was no reason for alignment, unless the alignment was generated internally. One theory now gaining traction proposes the presence of a coordinated electric field originating from within the nucleus of the object. If this field was oscillating at the right frequency, it could cause charged particles in the coma to align momentarily, creating a macroscopic polarization plane. This concept has only ever been demonstrated in lab-based plasma containment experiments, but never in the open vacuum of interstellar space, and then a pattern emerged. Archived polarimetric data from Atlas's earlier solar pass, weeks prior, showed no such alignment. The polarization effect only began in the last 72 hours, intensifying during the object's trajectory stabilization and tail compression episodes. In other words, it started when Atlas began exhibiting controlled behavior. The alignment of light wasn't random, it was part of a larger sequence, and there was more. Researchers from the Infrared Space Observatory noted that the degree of polarization varied depending on the observer's position relative to Earth's magnetosphere. This suggests that the aligned light was interacting with magnetic fields, meaning it had not just orientation, but spin characteristics. Photons can't acquire spin post-scatter unless the medium they pass through is actively modulating them. This implies that the coma of Atlas isn't just passively reflective, it's behaving like a structured optical medium. In essence, Atlas is now polarizing the light around itself, possibly as part of an active control system, one that may be using light as a navigation aid, a communication signature, or even a sensor interface. One senior astronomer remarked privately, "If this were a ship, this is the moment it turned on its targeting grid." To the public, no statement has been released. The official NASA bulletin classifies the event as a temporary linear polarization anomaly, but internally agencies are referring to it as an active polar alignment field, the kind of term only used in controlled systems research. This much is now clear. Atlas isn't just reflecting sunlight, it's restructuring it. And whatever is inside that coma now appears to be choosing what we see and how we see it. At 21:06 UTC on November 26th, a silent protocol was triggered at ESA's Deep Sky Observational Relay located in La Palma. The command came not from mission control, but from the telescope's autonomous system core, an automatic shutdown sequence known as Protocol Zeta 4, colloquially referred to as the telescope lockout. The reason, an input signal conflict between expected telemetry and real-time visual stream of 3I Atlas. In simple terms, what the telescope was seeing didn't match any known signature or forecast model. The object's observed movement, reflectivity, and thermal balance veered so far outside its predicted envelope that the system flagged it as malicious interference, as if the data feed had been spoofed or corrupted. But it wasn't corrupted. Multiple off-site backups from France, South Africa, and Antarctica's Dome Sea Observatory confirmed the same anomaly. This wasn't a malfunction. It was a coordinated observational dissonance, and the lockout was triggered to prevent further data passing without human override. Why would a telescope lock itself out? ESA's newer observatories are built with information hygiene systems, AI-guided routines designed to halt data processing when the incoming visuals risk corrupting predictive models. This is not for physical safety, but for algorithmic integrity. If the system observes something that defies physics too sharply, it stops processing to avoid training future systems on false premises. And on the night of November 26th, 3i Atlas did exactly that. The telescope reported reflectivity inversion across a 1.6 kilometer band phase lag between visual and infrared layers, frame-to-frame jitter in the object's outline without any detectable motion. In other words, Atlas looked like it was in two places at once, or flickering between configurations. That's not a comet. That's not even natural. Observers from the Madrid mission hub quickly rerouted access through a cold mirror override to re-engage the telescope, but they encountered a blackout zone. For precisely 184 seconds, the telescope received no photons from the object, not even scattered noise. It was like pointing the lens into a hole in the sky. Then, just as suddenly, the stream returned. Atlas was back. Same position, same orientation. But the reflective band around the nucleus had changed from a neutral grey to sharp green-blue, with no apparent cause. The telescope lockout was cleared, but by then something far more troubling had been discovered. The event time of the lockout matched exactly with a signal spike detected by ESA's S-band monitoring station in Turin, a signal that shouldn't exist in that bandwidth, and certainly not synchronized to a telescope input freeze. The fear now isn't that the telescope failed, it's that the object responded to the observation actively. Some are calling it a counter-surveillance event. Others believe the object emitted a targeted burst to either jam the optics or confuse the data pipeline. But for nearly 3 minutes, one of Europe's most advanced optical platforms chose to blind itself rather than process what it was seeing. This raises a chilling precedent. Not only might 3i Atlas be aware of our observations, it may now be interacting with them, and worse, it may understand exactly how our instruments work. This is not a blackout. This is a redaction. It didn't begin with a press conference. It didn't even begin with a leak. The first signs of unrest inside the scientific establishment appeared as a silence, a subtle shift in tone across data portals, project logs, and cross-agency emails on the morning of November 26th. Researchers who had been sharing hourly commentary updates suddenly stopped. Data streams went read-only. Access credentials were silently revoked. And internal Slack channels at multiple observatories, especially those coordinating on 3i Atlas, began logging ghost notifications. Open threads with no replies, file deletions without changelogs, visual models pulled offline, pending revision. This is not how scientists behave during breakthroughs. This is how they behave when the truth is too unstable to publish. By mid-morning, mission analysts at NASA's Jet Propulsion Laboratory began cross-referencing light curve deviations from Atlas with unrelated gravimetric data. But when the modelling software returned error codes, twice in a row, they didn't troubleshoot the software. They unplugged it. ESA's deep telemetry team went one step further. They air-gapped their modelling room, printing paper-only visual maps of the tail symmetry anomaly, and locked the files in a physical cabinet. One physicist at a Nordic observatory even wrote in their private lab log, "Whatever this is, we're no longer tracking a comet, we are tracking behaviour." But it was the private calls that told the full story. Within 24 hours, university leads across 6 countries received direct calls from space agency liaisons. Not written memos, no briefings, just personal, one-on-one messages to cease external commentary until further notice. No interviews, no theoretical modelling papers, nothing speculative, especially about intent. The term used wasn't classified, it was destabilizing, because by now the patterns were no longer random. Atlas was no longer just emitting symmetrical jets. It was showing signs of timed repetition, feedback to observations, and perhaps most troubling, deliberate modulation of its own visibility. When a system behaves like it knows it's being watched and adjusts accordingly, science loses its language. That's when panic begins. But it doesn't happen through screams, it happens through withdrawal. One spectral analysis team from Japan paused their project mid-run and scrubbed their GitHub commits from public access. They later uploaded an unrelated placeholder project, an old one with no comet relevance, to reset the file history. They called it Chiral decay test. Ignored dataset. It wasn't ignored. It was buried. Meanwhile, the James Webb observation schedule was suddenly shuffled. A full block of comet observation time was replaced with a placeholder labelled Mid-IR Survey of Background Dust Fields. But no new coordinates were entered, and the primary instruments were pointed at empty space. This wasn't a redirect for curiosity. It was a refusal to engage. The panic had begun, not through alarm, but through academic retreat. The final confirmation came through the quietest signal of all: silence in citation chains. Normally, when a comet shows irregular activity, thousands of academic footnotes begin propagating, adding to the network of open-source theories and collaborative refinement. But with 3i Atlas, the trail stopped. No new citations, no cross-acknowledgements, no updated forecasts, just a quiet ripple of intellectual withdrawal, as if the world's brightest minds had simultaneously chosen to pause, watch, and say nothing. That's not scientific fatigue, that's containment. Because in truth, the panic didn't start with what Atlas did. It started when scientists recognized a pattern, and patterns imply intention.